Alright, we'll get to sample problems in just a second. I just wanted to remind you from the intro video, the situation where we wanted to choose 3 things out of 10, but we didn't care the order. So it wound up being 10 factorial over 7 factorial times 3 factorial. And we pointed out, notice how 3 and 7 add up to 10, and that's going to happen every single time. So the formula here for NCR would be whatever n is, right? 10 was n in this example, just be n factorial over n minus r factorial. Now that's the exact same thing as permutations. But then, to get rid of all of the orderings, we will divide by r factorial. Okay, so this is our formula right here. So as we do any of these, that's going to be what we use. Alright, to start with, let's use number 5. 9c6. So like we said, this is going to be 9 factorial over 3 factorial times 6 factorial. Alright, the formula for combinations is so simple. You take the large number, n factorial, over this guy here, and then whatever adds up to 9. Very simple. Okay, so this would be 9 times 8 times 7, so the 6 factorial is canceling the 6 through 1 over 3 times 2 times 1. 3 cancels with 9, leaving 3. 2 cancels with 8. This is 4. So 12 times 7, which is 84. Okay, number 9. 7c5. It'll be 7 factorial over 5 factorial times whatever adds up to 7. That'd be 2 factorial. Okay, so this 5 is going to cancel out 5, 4, 3, 2, 1, so we get 7 times 6 over 2 times 1. 2 cancels with 6. This is 3. 7 times 3 is 21. Okay. Now, I would be remiss if I did not show you that your calculator is able to do this without you having to do the formula every time. And the way we do it is, you're probably not going to be surprised here. Not really going to catch you off guard. We go to Math, over to PRB, and then right under NPR, which we have been using, is NCR. So 7 NCR 5 is 21. Okay, so there we go. Alright, in number 13, we're looking at different hands, poker hands, 5-card hands. So we want to get 5 face cards. That's it. 5 face cards. How many different combinations are there of poker hands that are just face cards? And think about this, is order important here? Well, you get dealt 5 cards, no matter how you arrange them, it's still the same hand. Okay, so it doesn't matter the order that you get the cards in, it doesn't matter what order you put them in once you get them, so definitely we are using the combinations, right? Okay, so let's think. This number here is what we're picking out of. We're choosing out of 7 things, just in number 9, for example, and out of those 7 we're choosing 5. Well, in this example, we know we're definitely just picking 5 cards out of, well, out of what? That's the question. Well, we want to wind up with only face cards, so we better choose from things that are only face cards. How many face cards are there? There's Jack, Queen, King in every suit, 4 suits, 12 cards. Right? So we're going to choose, excuse me, out of those 12 face cards, 5 cards for a poker hand. So, what's that going to be? It's going to be 12 factorial over 5 factorial times 7 factorial. And rather than do all that, we can just do, let's bring this back up. That's going to be 12, choose 5, 792. Okay, and often That's how we say it. If you have a 12 C5, you say 12 choose 5. You're choosing 5 out of 12. So we just use that. C actually does not stand for choose, but that's what it brings up in people's minds a lot. So I will often say that. So now we want one ace and 4 cards that are not aces. One ace and 4 not aces. Okay, so well, we just talked about how to get 5 face cards specifically. So we could find out how many ways there are to get one ace, and how many ways there are to get 4 not aces. Okay. Now these are going to be 2 different events. The event that you get an ace, and the event that you get 4 not aces. Right? So that's going to bring back in the fundamental counting principle where, okay, so we're going to get an ace, and then after that we're going to get 4 not aces. Right? And then however many ways there are for this to happen times however many ways there are for this to happen. Right? If you knew that you could get an ace in 4 ways and you could get a not ace in 75 ways, I don't know how many ways there are, then you would multiply them together. Just like we did with the MacBook Pro example, there were so many screens that we could get, so many hard drives, so many processors, and we just multiplied it together. So same situation here. So now it just remains to find how many ways there are to get an ace, and then how many ways there are to get 4 not aces. Well, how many ways are there to get one ace? There's only 4 aces. There's only 4 unique aces that you can get, so that's pretty clear as 4. How many ways are there to get 4 not aces? Okay, so now we got this bigger pool of a bunch of cards that are not aces, and we're going to take 4 out of them. We're going to choose 4 out of that group. How big is that group? How many cards are not aces? There's 52 cards in a deck. 4 of them are aces, so 48 of them are not aces. Alright, so that's going to be 4 times, why don't we just do it all at once, huh? 48, or 4 times 48, choose 4. So, so 778,320. Next, let's do number 16. 5 hearts or 5 diamonds. 5 hearts or 5 diamonds. Okay, so, but it's this or it's this. This has a number of hands it could possibly be, and this also has its own number of 5 hands, or number of hands of 5 cards that this could possibly be. So what would we do with those 2 numbers? If I knew how many hands had all hearts and how many hands had all 5 diamonds, what would I do with those 2 numbers? Would we just add them together? We want to know the total of those hands. We're just going to add them together because they're not happening at the same time. Right? So my point here is that we're not going to multiply them together. Here, these happen at the exact same time. These are part of the same hand. These are 2 different kinds of hands. Right? Somebody over here could be getting all hearts, somebody over here getting all diamonds, and then we add them together to see how much we have all together. Alright, so we know we're going to, the order doesn't matter, we're going to choose 5 out of how many? Well, how many hearts are there? There's 13. And same for diamonds, there's 13 diamonds, when we pick 5 of them. So we could just do 2 times whatever this is. So let's find out what this is. 13, math, PRB, combinations, 5. So it's 1287, 2 times 1287, and that is 2574, 2,574 hands, being hearts or diamonds. So distinction between or and. These happen at the same time. These don't necessarily happen at the same time. They're 2 completely different scenarios. These are part of the same scenario. Okay, 36. Now here's the tricky part. We know how to do combinations. If you tell me to do combinations, I'll do it. If you tell me to do permutations, I'll do it. But how do you know whether to choose permutations or combinations? That's the tricky part. Choosing between the two when either of them are in the mix. Either of them might be the answer. So in 38, your school newspaper has an editor-in-chief and assistant editor-in-chief. The staff of the newspaper has 12 students. In how many ways can students be chosen for those two positions? So the way that I remember is permutations is a word that means unique orderings, right? So if I'm going to use NPR, do I use NPR? That's the question. Do I use NCR? We're trying to figure that out. P is a word. Permutations, or P stands for the word permutations, and permutations means unique orderings. When you permute things, you reorder them. Combinations, there's nothing about that word that says to me we're going to reorder things. Just going to combine them into different groups and count those groups. So permutations is where order is important, and combinations is where order is not important. Is order important in this scenario? Anytime it makes reference to different positions having different names or different significance, we're at least start to wonder if there's importance in the order. So when it says editor-in-chief and assistant editor-in-chief, and you think about two people who are assistant editor-in-chief and editor-in-chief, and if you switch them, if you change which place they're in, does it make a difference? Yeah, it does. Now the person who is assistant now is the editor-in-chief and vice versa. So order is important here. They fill two specific positions that have different names and different roles. So order is important in this situation. All right. So we have 12 students on the staff of the paper. We're going to choose 2 of them to be in these 2 positions. So that's 12P2. Here we go. 12 math over to P2, 132. There we go. 37. Oh, 37. What did we just do? This was 38. My apologies. This is going to be 39. So 5 representatives from your senior class of 280 students are to be chosen for the student council. In how many ways can students be chosen to represent the senior class in the student council? So does anything about that make you think order is important in this situation? They must be in a specific order for this question to be answered. Nothing about that tells me anything about order. There's no names for the council members, and they're just going to be the senior representatives of the student council, and then there'll be junior, sophomore, and freshman representatives. So it doesn't sound like, it sounds like maybe like some kind of a democratic process, and they just kind of vote on things and decide things together, collaboratively. So there's no order that's important, so we're saying NCR, combinations, not permutations. Order, not important. Okay. Let's see, 280 students to choose from. We're choosing 5 of them. 280. Choose 5. That's a lot. So what does 10 mean? It means move the decimal place 10 places. So let's start. I mean, we could do this, 1.38 times 10 to the 10th, or we could get a feel for how big this number is. Okay, we're going to move it over 1 position, so 1, 2, 3, 4, 5, 6, 7, 8, 9, and when we don't have anything left, we'll just put a 0 on there, 10. So, see, thousands, millions, billions, over 13 billion ways to do this. Pretty spectacular. Okay, now Let's do number 49. And this is the illustration they give us. Let's make sense of this illustration. What do they want us to do? You want to get 3 CDs. That is all. You just want 3. From an online collection that contains the types of music shown at the right. And so this is the picture they have. You want each CD to contain a different type of music, such that 2 CDs are different types of contemporary and 1 CD is a type of classical music. Classical music. So, how many different sets of music types can you choose? Alright, so we want 2 things to come from here and 1 to come from here. Okay? So, however many ways there are to get 2 CDs, contemporary, and then however many ways there are to get 1 CD classical, however many ways there are for this to happen times however many ways there are for this to happen. Right? It's just fundamental counting principle. That's what we're going to do. We're going to multiply those 2 things together. Now we have to find out how many ways are there to get 2 CDs to be contemporary. We could choose blues and country, or you could choose country and rap, and so on. How many different ways are there to pick 2 out of these 5 things? So that's combinations. 5, choose 2. How many ways are there to pick 1 CD out of the classical? Well, you pick opera or concerto or symphony. So there are 3, just 3. So we would multiply these together. Let's use the formula, because it's just pretty small numbers. So 5 factorial over 2 factorial times 3 factorial. We're going to multiply that by 3. Let's let the 3 cancel out the last 3 here. So we got 5 times 4 over 2. Multiply that by 3, cancel 2. 10 times 3, 30 ways. Okay, there we go. That's the last one. Thanks for watching.